All right, so we're comfortable with concepts of delta G, enthalpy, and entropy working together. We're comfortable with that? Okay, so the card to say before I decided to record. Remember, when we have a system at equilibrium, we have products that are moving at a rate towards reactants, and reactants that are moving at a rate back to products. Remember that? So the definition of a system at equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. And for that value, we have a K value. I'm just going to call it KQ. Remember, we can have KP or KC. KP when we're talking about gases, KC when we're talking about concentrations. Okay. And that is, I'm going to go ahead and use the concentrations here, the concentration of the products over the concentration of the reactants. Okay. Are we comfortable with these concepts? Because that's at the heart of this unit. When you have a system that has a delta G value that is negative, we call it spontaneous or product favored or a thermodynamically favored system. In other words, if our delta G is negative, delta G is negative, this is a thermodynamically favored system, this is product favored, and energy is going to be released out of the system. Okay. For a negative delta G, the negative means that the system will release energy. If you release money from yourself, you have a negative delta money. Capiche? Okay, so if a system has a negative Gibbs free energy, this is a thermodynamically favored system. We say it is a product favored process, and it is going to release energy. Understanding that, the system cannot be at equilibrium. Because if the system is equilibrium, the forward reaction and the reverse reaction are happening at the same time. So think of a system at equilibrium as one that appears to be settled. We realize it's a dynamic equilibrium. The forward reaction is happening at the same time as the reverse reaction, but looking down at the beaker at the macro scale, it doesn't appear anything's happening. So if our delta G value is negative, Gesundheit, what can we say about the K value? What can we say about the equilibrium constant? Larger than 1. Exactly. It has a larger numerator than a denominator. We're going to find out there's some nuance to the number, but let's go ahead and just use the larger, extra larger than 1. So if we have a Q value, if we have a G value that is negative, we have a K value that is larger than 1. Has to have a larger numerator than denominator, right? Wrong. Because if your K value is larger than 1, that means your numerator is too big. If your numerator is too big, what direction is the reaction proceeding? Towards the reactants. So, if the reaction is proceeding towards the products, then the K value must be what? Less than 1. In other words, if the reaction is proceeding towards the products, if it is product favored, that means the system is not at equilibrium, and the system is proceeding towards the products, which means our reactants are too big. Remember the Q value? If a system is at some point in time, we have a Q value that has the same math as the K value, but the Q value is at some point in time, and it will proceed towards the K value. Does that concept make sense? Because again, this ties in the last 3 big units in AP Chem into a reasonable concept that we can use to make decisions about what's going on with a reaction. This is why this is one of those bellwether units that you absolutely have to know. This is going to separate the 4s from the 5s. If you understand what's going on in equilibrium, then you can understand what's going on with the reaction and how much energy is going to be released. So, in summary, if your delta G is negative, that is a forward reaction favored process. Jeez, you guys never pointed out that I wrote this wrong. No wonder Lane got it wrong. Reactants and products are backwards. Now it's like Lane's like, that's what you got it all backwards. You got me backwards. So reactants go to products. If your delta G is negative, you have a product favored process. We say this is thermodynamically favored. It's going to release energy. That's what's going on right now in your pockets and your calculators. There's a reaction that's proceeding. It is producing energy as reactants become products. So it can't be at equilibrium. If it was at equilibrium, then neither the forward reaction or the reverse reaction would be favored. So we have a system where we have way too much reactants. It's proceeding towards products. We have to talk about the reverse of that. If the delta G is positive, we say it is reactant favored. We say it is not thermodynamically favored, or we say it is thermodynamically unfavored. If you're gonna, by the way, if you're gonna write down thermodynamically unfavored, make sure your handwriting is really good so the reader sees the un in front. So if you have a positive delta G is positive, this is thermodynamically unfavored, this is reactant favored, and energy must go into the system. And that means that what side of our equilibrium expression is larger? Does that mean we have too much product or too much reactants? We have too much products. Okay. So if we have too much product, that means our K value is way too big or too small? Bigger than 1 or smaller than 1?
Small.
Bigger than 1. Too much product.
Oh, yeah.
Our K value is larger than 1. Okay. How are we doing? Should we move forward? All right, so delta G and KEQ, they have both a conceptual relationship and a mathematical one. So remember, delta G must be less than 0 for reaction proceeding in a given direction, the maximum amount. So when you talk about what delta G is, if somebody was to ask you, define delta G, and you responded with Gibbs free energy, I would say that's probably not going to earn you any points. So in your own words, what is delta G? What does it represent? Audience participation. Change in energy? Okay. If you see a delta G that is positive, what does that tell you about the reaction? Okay. Delta G is positive.
Endothermic.
Delta H determines whether it's endothermic or exothermic. So if your delta H is positive, it is endothermic. But if you have a delta G that is positive, that system what? In order to continue? Requires energy. So if you have a system that has a delta G that is positive, that system requires energy to proceed. That's what happens when you want to recharge your battery. Like my phone's plugged in right now. I am reversing the chemical reaction in the little battery. I am recreating the reactants, but in order to recreate the reactants, I have to send energy, a continuous flow of energy into the battery. That's our delta G. Gibbs free energy is the energy required or available for the process. A positive Gibbs free energy requires energy for the reaction to proceed. A negative Gibbs free energy releases energy as the reaction proceeds. Cool? Okay. What we will learn today. Okay, so if a system is in equilibrium, it is not moving forward or reverse. if the system is equilibrium, at equilibrium, we have a situation where the forward reaction and the reverse reaction are occurring at the same rate. It is neither product favored nor reactant favored. So that's when we have a delta G that is 0. Again, the inflection between a negative and a positive delta G is 0. So if we have a delta G that is 0, the system is neither product favored or reactant favored. That means, with some nuance, we have a system at equilibrium. I say with some nuance because there's a little math we have to get into, but the AP is not going to worry about it. Unfortunately, the author does add the nuance, but the AP will not. Okay, so this is kind of neat. How do you read this graph? Basically, this graph means if you have all A, this is the amount, it says combination of, can I just use ratio of A to B, all A to all B? So on the x-axis, we have all A, all B, and then a mixture of A and B in between. If we have all A, then the reaction is going to be very, very what favored?
Product favored.
Product favored, because we only have denominator. Remember in K, we have our reactants in the denominator. So if we have a whole bunch of A, then all we've got is reactants. We have an extremely small K value. The reaction is going to be product favored. Are you comfortable with this concept? Okay. Now, as the reaction proceeds over time, it goes from very, very, very product favored to less product favored, and over time becoming more and more reactant favored. In other words, as the reaction proceeds, we consume our reactants and produce our products until we get to a point where we have more, or actually we have equal amounts of A and B. That's our equilibrium. And then if we continue on on the x-axis, now we have more B, more products than we have reactants. So this unshown line here, that's your 0 right there. Okay. Where it hits equilibrium, that is our delta G equal to 0. Everything above this, our delta G is negative. Everything below it, our delta G is positive. Can you conceptualize that has a y-axis that's upside down? Where everywhere that is thermodynamically favored, that it is product favored, product favored, product favored, product favored, this is all delta G that is negative. Product favored, product favored, product favored. At equilibrium, delta G is 0, and then reactant favored, because now we have too much products, and from here down, our delta G is positive. Are we comfortable with this? Questions? So here's an explanation again from, let's forget that, it's not important. All right, process favors products, delta G is larger, KQ is too much, exergonic, yeah, gotcha. All right. More stuff. Yeah, don't endergonic. That's sometimes your author gets a little wonky because he's in his 70s. So when he wrote this, he was in his 60s. So don't use exothermic and endothermic for enthalpy, but then use product favored, reactant favored, requires energy, produces energy. Hey, look at all that stuff. Okay, so here's the cool formula. Delta G equals negative RT natural log K. Now you can learn this two ways. You can learn this the way I learned it, plug and chug. Or you can conceptually understand what this means. Plug and chug requires more time because it requires you to do the math for A, B, and C, A, B, C, D. But conceptually understanding it makes more sense. So what does this mean? ln's a natural log. Okay. A natural log of a very small number is positive or okay. A natural log of a number less than 1 is positive or negative. Any logarithm less than 1 is positive or negative. Negative. So in your calculators, put in logarithm of 0.1. Any log, natural logarithm is still a logarithm. It's just not base 10, it's base 2.7 something. So in your calculator, do logarithm 0.1.
You guys want calculators?
-1.
-1. Okay. So the logarithm of any number smaller than 1, whether it be a pure base 10 logarithm, log, or a natural logarithm, this is logarithm base e, might be having a stroke, but I think it's 2.7. So the logarithm of any number less than 1 is negative. The logarithm of any number larger than 1, do logarithm of 12.
1.08.
Positive. Okay. So logarithm of any number less than 1 is negative. The logarithm of any number larger than 1 is positive. So if you take a forward reaction favored system, remember, forward reaction favored means there's more reactants than there's products. So if something is forward reaction favored, you're going to have a small k value. If you have a small k value, the natural log of k is going to return a negative number. Right? Okay. Negative RT, temperature has got to be positive. R value. Okay, so remember in gas laws that R value is 0.0821? And I told you last year that that's because chemists don't like to use standard units. You have to use the standard R value for this calculation. And the standard R value is 8.314. Okay. So, if you have a K value, what this formula means, if you have an equilibrium constant value, then you can plug your values into this to get what delta G would be, which is literally how much energy you can harvest from the system. And again, we use the K value, but remember we have Q values, Q and K. Q is at any point in time, K is the actual reaction. But if you have the K value, if you have a number, a K value, that is very, very product favored, this number is going to be positive. This number is going to be positive. This number is going to be positive. Your delta G value will tell you you can harvest a whole bunch of energy from that reaction. A product favored reaction, or a reaction that needs to move towards products allows you to harvest a lot of energy from the reaction. Does that make sense? So I'm going to set this reaction up. The reaction, when it reaches equilibrium, regardless of where it is now, when it reaches equilibrium, there's going to be a whole bunch of products. That means your K value is going to be very, 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 very big. So if your K value is going to be very, very, very big, your natural log value is going to be positive. Your T is going to be positive, it's in Kelvin. Your R is going to be positive because 8.314. Your delta G is going to be negative. So regardless of where you are, if your equilibrium, when it reaches equilibrium, will be mostly products, you can harvest energy from that system. And you can calculate exactly how much energy you're going to harvest from that system in joules per mole. Okay, so far so good? By the way, I mentioned this, I wrote this in my notes, I need to mention it. What you get from this is joules per mole. Delta G, when we're using Gibbs free energy formula, delta H minus delta S, is going to be giving us the formula in kilojoules per mole, because again, chemistry like to use non-standard units. But this gives you joules per mole, because the R value is in joules. Let me show you what I mean. I'll write this out for you. You can't see it in your mind's eye. Hopefully this will help. The R value is joules per mole Kelvin. The T value is Kelvin, and then the KEQ is just a number. Natural logs do not return units. Does that make sense? So canceling this out, your G value returns a number that is joules per mole, not kilojoules per mole. This is super important for the formula, for the homework you're going to do tonight. Because a lot of you are like, I keep doing the process, but the numbers are wrong. It's because the delta G that you looked up was given to you in kilojoules. You need to plug it into the formula and turn it into joules. It's really annoying. Again, when you do the formula we use, delta G equals delta H minus T delta S. Delta G is given you in kilojoules. Delta H is given to you in kilojoules. This is Kelvin, and then this is joules per mole, which needs to get turned into kilojoules. So that's a conversion you need to use. The other conversion you use is if you use this number and plug it in here, it needs to be converted to joules per mole. All right, cool? Now, on the other hand, okay, any questions about this before we move forward? On the other hand, if you have a system that regardless of where you are in Q right now, Q, regardless of where you are, if you have a system that is primarily reactant favored, then the system's going to require energy to get there. It's going on right now on my phone over there. I have a system that is reactant favored, which means my K value is very small. The natural log of K is going to return a negative number. Temperature is going to be positive. R value is going to be positive. Negative of a negative is going to give us a positive delta G number. So if we're starting the reaction, regardless of where we are with Q, we're going to move towards K. Hang in there, Soph. We're going to move towards K. If we're moving towards a system that is reactant favored, that's going to tell us how much energy we need to supply to get to that point in joules per mole. And by the way, you guys realize that ln is logarithm base e? The reverse anti-logarithm is 10 to the whatever it was. It's like logarithm base 10, the anti-logarithm is 10 to the negative whatever. Okay. Or sorry, 10 to the whatever. In this case, if you are doing the reverse logarithm of this, then it's e to the negative delta G over RT, which I believe the first one is given to you and the second one is not. Yes. Okay. So to add a little pain to your process, that is given to you on your formula chart. That is not. You are just, I want to say that I've never seen them actually having to use this on the test. This you've had to use before. But if you should be, they are expecting you to understand how logarithms work. You know, like P and pH and stuff, turning that pH into a concentration. So if you need to do the reverse of this and get K from G, that's how you do it. You divide both sides by RT, negative RT, and then you invert the logarithm. You do the anti-logarithm. So you can kind of see delta G divided by negative RT becomes this. Anti-logarithm of the natural log is e to that thing. Okay, now here's that nuance I told you about. I said that delta G positive or negative. Technically, it's positive or negative 2400 joules per mole. And that comes from the, they can round it up, 8.314 times 298 Kelvin. Why do they do that? This 8.314. 8.314 times 298 Kelvin, 2477. Yeah, I don't know why the author did that, but it's 8.314 times 298. Standard temperature. Temperature at that little delta G zero. So anyway, so it's technically not delta G is positive and not delta G is negative. It's delta G larger than 2400 joules per mole and delta G smaller than negative 22,400 kilojoule or joules per mole, which is larger than 2.4 kilojoules per mole and smaller than negative 2.4 kilojoules per mole, which is a very, very small window. Effectually zero, but not. Does that make sense? Context clues, you won't encounter this. You won't encounter that level of nuance on the AP. It'll give you a number that's like positive 150 kilojoules per mole. So a positive 150 kilojoules per mole for a delta G would mean you have a K value that is what? Very big or very small? Positive big kilojoules per mole. K value must be small, much less than 1. Or they'll have a value of delta G that is negative 250 kilojoules per mole. Negative delta G means your K value must be very, very what? Much larger than 1. Okay. This level of nuance is just because the author wants to be accurate. And technically that whole RT is about 2478. All right. If you're comfortable with this, give me a thumbs up. Because we are almost done. Okay. So that's the bulk. That is a very valuable equation. That relationship is very, very valuable. That if you have a process that is going to be moving towards the products, it's going to have a K value that's very, very small. Sorry, a K value that's very, very big. A Q value that'll be very, very small. The K value will be very, very big. A big K value means your delta G is going to be very, very negative. A big K value, regardless of where you are in Q at one point in time, if the process is going to move mainly towards products, you're going to be able to harvest energy from that. You have a negative delta G. On the other hand, regardless of where you are with Q, if the reaction is going to proceed primarily to reactants, you're going to have a K value that is very, very small. You're going to have a delta G that is very, very positive. It's going to require energy. So again, should I get chug? You can learn it that way. Or you can realize that if a reaction needs to go forward, or if the reaction will eventually go forward and be product favored, it's going to give you energy. If the reaction is going to go reverse and be reactant favored, it's going to require energy. Okay. So there's what we just said in a table. Here's a sample exercise. Let's go ahead and do it. For a certain reaction, so this checks all the boxes. For a certain reaction, delta H is negative 20 kilojoules. Exothermic. Is an exothermic system thermodynamically favored for enthalpy? Yep. And the delta S term is negative 400 joules per Kelvin. Is that a thermodynamically favored system for entropy? No. In this case, entropy is decreasing. So we have a system where the enthalpy and the entropy are at odds. Temperature will tell us whether the reaction is going to be a forward reaction for reverse reaction. So we're going to solve for our delta G. Then we're going to use that delta G to determine what K is. And then we're going to answer the question. So do that now. Really hope this is more of a nuance. Because I don't remember if it is or not. After you finish your process, chat with your neighbor, figure out which of these statements is true. I think it's only one of them.
Call to fill set it the other way.
Yeah, okay, so only one of these is correct.
I'm at 2. So 20,000. Yeah, but it's negative. This
So,
is
in pieces, what did you get for delta G?
2.
Positive or negative?
Oh,
Positive. Positive 99.2 kilojoules per mole. Which, again, if you want to continue the mathematical process, you can totally figure out what K value is, but you don't need to. Because all you need now is that G is very, very, very positive, which means this term, negative, positive divided by positive times positive. See what I just did? Okay, so again, you can bang out the calculator and just find out what the R value is or what K value is and be like, okay, I did it. But since you have a minute and a half per question, I would stop right here and realize that you have a positive delta G divided by two positive numbers, 8.314 and 298. Right? 25 degrees, yeah, 298. So this gives you a negative number in the exponent. Anything raised to a negative number is what? That's a magnitude question. Do 5 raised to the negative 100. No, doesn't matter. Anything raised to a negative number.
It's smaller.
Paquito, exactly. So anything raised to a negative number is going to be Paquito. So even if it's E 2.7 raised, so you have raised your E value to a negative exponent, that tells you the K value is less than 1. Okay? So if our K value is less than 1, you have a product favored system or reactant favored system? Reactant vapor system. Once again, for those like me who need a visual system, you have the products on top and the reactants on bottom. If your K value is really small, you have a system that is tiny products and really big reactants. Reactant vapor. This is a reactant vapor system. So regardless of where we start in Q, the system is going to move towards the products. C. Sorry, reactants. 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 Did I just say reactant? I've been saying reactants this whole time, right?
Yeah.
Okay. So regardless of where we started with Q, the system is going to move mostly towards reactants because you have a very small number. That means you have a bigger denominator. So C is the only one that is applicable. Context clue in a second. If you have a system that's asking about equilibrium, D is never going to be correct. If the system asks for equilibrium, going to completion will never be the correct answer. Just won't. Always going to be there as a detractor, even if it's a hugely positive if it's a hugely positive K value, it still never goes to completion if the system's asking about equilibrium.
If you were gonna solve for K using that, does delta G have to be in joules?
It does.
Okay.
Yeah, so if you were solving for it, the math would look like this. It would be E raised to the negative with the whole mass in parentheses, 99200 divided by 8.314 times 298. It would look like that. Whatever that is, I don't even know what that is. I don't care what that is. Okay. Are we comfortable with what we just did? Feeling good about this? Further questions? All right, moving right along then. Do we have everything else? Or the same, or the same? Conceptually, more of the same. So given delta H, given delta S, find the value at KP in order to find the value, find G. So this one's actually asking us for the actual number. I feel like we can skip this because it's in your homework. I'm wrong, let me know. Or the same, or the same. Okay, so the rest of this unit is about dissolution, and we can sum up what we need to know about this by remembering what has to happen in dissolution. So it's a little bit of a review from unit 6. So let's go there because it's super important. If you have sodium chloride, 3 processes need to happen. First, we need to break the sodium and chlorine attraction, the sodium ion chlorine attraction. Then we need to break the water molecule attraction. Then we need to form the chlorine water sodium water attraction. That's probably what happened over years is magnets, when magnets get hot or when they get impact, they lose their magnetism. Lane knows about this, he took physics. So probably this got dropped a number of times, it just doesn't want to stick very well anymore. Anyway, 3 processes have to happen. Break the ion-ion attraction. Break the water molecule attraction. Form the water ion attraction. And if you remember, delta H can be calculated by bonds broken minus bonds formed. So remember, delta H equals bonds broken minus, I should probably write the whole thing out, bonds formed. So, break ion-ion. Break water H2 bonding. Form ion dipole. So in order to dissolve something, you need to break the ion-ion bond. You need to break the H2 hydrogen bonding. Then you need to form the ion dipole bond. So far so good? Now, why am I reminding you of this? Because we know that +1 metals with -1 nonmetals are they're always soluble. I can't think of a single time where a +1 metal and a -1 nonmetal is not soluble at normal room temperature. That would be a delta G that is what? If something will happen on its own without additional help, as a delta G is positive or negative?
Negative.
Negative. Okay. So technically speaking, you can harvest energy when you have something that is very, very soluble. It has a delta H that tends to be exothermic. Or in broad senses, something that is soluble, +1, -1, it will dissolve on its own. But we know that +3 metals and -3 nonmetals are always insoluble. So soluble, NaCl, +1, -1. Insoluble, Al, aluminum phosphide, +3, -3. Why does aluminum phosphide require a lot of heat to dissolve into water? One of these terms is bigger than the other ones. Exactly. So because of Coulomb's law, remember Coulomb's law? So Coulomb's law is the force of attraction, electrostatic attraction, is equal to K Q1 Q2 over D squared. Because of Coulomb's law, the force of attraction of a guys, you could let me know when I'm making a mistake. You do this to math teachers all the time. So when you have a +3 -3 salt, this ion-ion attraction that must be broken is much, much larger than in a +1 -1. Make sense? So what happens is you go from a system that is normally exothermic or negative with a +1 -1, where this is larger because this is smaller. This is going to be constant. Okay, breaking the water molecules, hydrogen bonding is going to be constant for all water molecules. But you go from a system that is normally exothermic, normally spontaneous, normally thermodynamically favored, and it will happen without our help, dissolving of a +1 -1. Because this value is bigger than this value, therefore negative, to a +3 -3, where the ion-ion attraction becomes so large that the delta H becomes positive. In other words, for a +3 -3, the ion dipole attractions that are formed are not large enough in energy to overcome the magnitude of the ion-ion attraction. Maybe I can show it visually. Different colors here. So for blue, ion-ion, so we're going to break the ion-ion. Okay. We're going to break the H2O hydrogen bonding. And we're going to form the ion dipole attractions, and the overall delta H is going to be negative. Can you see the conceptual math? Now, with aluminum phosphide, +3 and 3, ions not drawn to scale. In fact, let's draw the ions to scale. There we go. +3 -3. we have the same size hydrogen bonding. Alexa, stop. We have the same size, well, For the purposes of our discussion, we have the same size ion dipole attraction. Is it exactly the same? No. But do we care at this point? No. But what is very, very different is the massive ion attraction that must be broken. The result is that larger ion attraction makes our delta H positive. Okay. Are you comfortable with this? All right. That pretty much checks all the boxes. Again, your author goes into some considerable nuance with entropy and stuff that we don't care about. And I think there's a lot of them we should do together, but I think you guys.
Yeah, not bad.
It worked the whole time. It did, yeah. There we go. Bye, Kane. Bye, Kane.